among multiple copies of the same cache line is to make sure when someone is updating that cache line, there is only one copy in the entire system. And that's a write-invalidate based approach. We could do others. We could do updates, although it's generally more difficult to do that. Every time someone updates the whole one cache line, make sure every other copy in the system is up to date. So that's usually not implemented and discussed. So we're going to look at the implementation. And there's lots of detail about this. This is, like I said early in the course, this is more of a hardcore, more detailed look at all these issues. So there's the general, there's the basics. How do you do this? You can do it via snooping, or you can do that with the help of a directory. And then there are all these sort of subtle issues to consider: the timing, race conditions, transient states, and speculation. Don't forget your underlying microarchitecture may be heavily speculative executed design. And we'll also get into a little bit about the notion of coma style design. So let's get started with the basic support. Okay, so remember this idea that, or this initial example, if we have a processor that updates a cache line and then someone else in the system is trying to read, we have to provide the up-to-date data, not the one that is in memory. And this providing the update is called intervene. To make sure that that's the only line in the system, we have to go through invalidation when we issue the write request. So this is what we want to do. The concept is simple. We want to do this so long as we do these. When you write, you validate all copies. When somebody wants to read, you provide the copy. So long as you carry out these actions, you'll be fine. But how do we do that? Okay, when do we know to invalidate? How to intervene? When? So pause a moment and think about how you would do it. How would the cache controller be able to tell, I need to do this and I need to do that? So if your answer is we need to keep track of it, and that would be the right answer, we need to have states associated with the cache line. If the cache line is, there are multiple copies of the cache line in the system, we know that. And therefore, when we want to write, we cannot just go ahead and write, we have to invalidate. On the other hand, if we did invalidate other lines, in the system and someone else is reading, we need to intervene. So we need states to make that happen. So the simplest states, and I mentioned that these are stable states, we'll see soon. There are other states called transient states. And typically the coherence protocol is referred to by their stable state. So MSI, the modified, shared, and invalid, is perhaps the simplest state. Okay, so it's fairly straightforward. In your uniprocessor design, the canonical cache design, you have a valid bit to say if the cache line is usable. Okay, and even in that case, you have a dirty bit to indicate that it's different from memory. So we are basically just taking those, but instead of having a dirty bit and a valid bit, we're taking all these different combinations and name them into 3 states. So if the data is invalid, we're in I state. Okay, so that's one of the circles over here. And in this state diagram, the black letters and arrows indicate the transition from state to state based on self-action. Meaning, suppose I'm in an invalid state and I want to read. Well, I'll go to the system and read. Right? Go to memory subsystem, bring in the line, and then I have the line in shared state in this new state, and that's what's shown here. So maybe I should use different color, not to so if you issue a read, the next state, after some action, of course, which is not shown here, after some action, the state would be transferred into shared. And if you're in shared state, subsequent read would stay in that state. Okay, so this is self-action, meaning what this state here, MSI, are describing the cache line in a particular processor. And if that processor issues read and write, this is what happens. On the other hand, the red color letters and arrows indicate external action. So this is a multiprocessor. There are other processors issuing read and write, and what we have to react to that. So there aren't that many transitions. Let's go through all of them. We just went through the read transaction if I am in I and then in S. So the shared state is really just like the name suggests, that there are potentially multiple copies of this cache line in other processors. We're all reading. Remember, if we're just reading, there's no coherence problem. We won't get into multiple different versions. So that's fine. You can read, everybody can read. The problem comes when you have a write. Either you don't have a valid copy, so you're starting from the I state over here, or you're already having a copy in the shared state. In either case, when you want to write, this is when you have to invalidate other copies, remember? Because there are potentially other copies in the system, and if you write, we start to get into incoherent state. So in both cases, if you want to issue a write, we have to go into a different state. Okay, we have to do something before we go into that different state, which is to invalidate. So in all these cases, we have to invalidate. Okay, once we invalidated every copy out there, we are in the modified state. And if we're in the modified state, now it doesn't matter if we keep on writing to it, because we know we're the only one. So modified implied that we have the only copy in the system. So conversely, if you are sending the invalidation, so if you're writing, what about that someone else who has a copy in its cache? And that's where this red W comes in. So suppose I am processor 2 and I have a cache line in the shared state, and now someone else, processor 1, issues a write request, and therefore it's going to invalidate me, and I will invalidate my line, and the result of that is my state is going into the right state into the invalid state, sorry. Okay, so that's easy. If I am already in modified state, okay, someone else issues a read, what happens? Think about it. Pause the video if you need. The answer should be intervene, right? That's what we said kind of early on. If you, if this processor starts to read, we have to detect that over here and intervene and supply the data. So you see, if we're in a modified state and there's a read request, and let's just write it here, we have to intervene. Right? We intervene, supply the data, and because now both that processor and the supplier have the same copy, and logically, we go back to the shared state where nobody can write. Okay. Now, one last request is, what if I'm in modified state and someone else wants to write? Again, pause, think about what you should do. So this is essentially two operations combined into one. This is just like the intervene that we just discussed. So if you're writing, you need the cache line to write. Okay, so I will supply the cache line to you, and that's the same thing. That's also intervene. And you can imagine us getting into shared state. So both processors have the cache line. But then again, this new requester isn't satisfied with a shared line, and it wants to write. So what we do is we have to self-invalidate. We have to take my line and move it into shared state, so this other node can get into modified state. And this is also shown here. If I'm in a invalid state to start with, this state, and we do a write, okay, we're essentially invalidating whoever has it, and that may be a person or a cache that has a modified data, so it needs to write back the data to memory, send a new copy to me, and at the same time invalidating themselves. Meanwhile, I, the request, the issuer of the write request, will go into the modified state. I hope this is clear. Draw this out yourself, and it will help you understand. So this is the simplest state that you can have to maintain coherence. We'll see that nobody uses this. There's always complications, optimizations, and the first thing to think about how to get this right is to know that you need to maintain correctness. So what are the correctness considerations? You should maintain a habit of thinking about these. First, you have to fulfill the condition for coherence. Remember, coherence involves write propagation, write serialization, and if you have a consistency model, you need to fulfill that. For instance, for sequential consistency, you need to guarantee write atomicity. So it depends on the consistency model. And when you're trying to carry these operations out, you may be getting into these different situations that you want to avoid: deadlock, live lock, and starvation. So we'll go through each of them. The deadlock part is kind of easy, and if you think about this, this is a picture that we're showing here, assuming we have 4 trucks coming from 4 different streets at the intersection. Suppose they happen to be in that particular state, and you can see they're deadlocked. No car can go forward. Okay, and that's because there is a cycle of resource dependency. I'm depending on you, you're depending on him, and so on. You may think this is silly, it doesn't happen. It does happen. There's plenty of chance that this happens. One example in a computer system is, suppose I have two nodes with some buffers, and each want to send another request. But because the buffers are full, we cannot send the request or reply. We cannot send anything to the other. Conversely, the other person couldn't send this to us, right? My real-world example is, suppose you and I want to exchange fruits. I have 2 apples in my hand, you have 2 pears in your hand, and the condition is this: you cannot have 2 pieces of fruit in your hand at any moment in one hand. So how do we exchange? Just using hands. You cannot put it on table or anything else. Okay, so we have a deadlock. Unless I give you one of my apples, I do not have an empty hand to take your pear, and vice versa. And that's a deadlock, and it does happen, and we will see examples of that and how to solve that problem. So, but that's the concept of deadlock. There is a resource dependency. It forms a cycle. And nobody can make any forward progress. All system activity ceases. Live log is slightly different. Let's come back to this example where we have the 4 trucks. Well, you say that's easy, okay? If the trucks back up, okay? In particular, let's say this truck backs up to here, and then we can proceed. Fine, it works. But how do we know that, right? You're designing a system where each individual agent is acting on itself. So let's say everybody involved in this case is autonomous vehicle. They all recognize, oh, we're in a deadlock. So what do? The minute I realize I have a deadlock, I go back. Okay, I back exactly some distance back to the beginning of the intersection. Okay, and once I get there, I wait for 2 seconds and I go forward again. Imagine that. What do you think would happen? And imagine the situation is so coincidental that all 4 trucks arrives in this position exactly at the same moment. And you will see, if that's the case, everybody would back off at the same time to the same location and wait for the same time and come back again, and they will arrive at the situation again. Okay? So then what is really happening is everybody is making some activity. This is different from deadlock, as in we're not sitting there doing nothing. We're all doing something. We're all trying to solve the deadlock. But it's a live log in that it's infinite loop with no real forward progress. Okay, so we do have problems like that. And finally, a much weaker issue of that is starvation. And this would be, if again we treat this truck problem, if the truck that we just drew here took the step back, only that truck. Suppose there's an external agent that says, oh, too bad, it's the truck that came from the south that has to go back. Fine. Once that truck retreats, everything else moves, and the truck would wait for a little bit and then come back again. And guess what? 3 new trucks came from a different direction. This is a busy intersection. We got into deadlock again. The south coming or the north going truck would be selected to backtrack again. And in that case, this particular direction would not make forward progress, but others do. Okay, so it's no longer a live log of the system. It's sort of a localized live log for one particular node, and that's called starvation. So you have to avoid all these situations, and that would be a correctness problem. You have a system like that, your system would have a thread that wouldn't make forward progress, and it didn't violate sequential consistency. It didn't violate your contract. You don't have a coherence problem, but the system is still incorrect. Nobody wants to buy a system like that. So those are the things you need to worry about. Now, I said MSI is the simplest possible. There's a very common optimization, and you see this type of protocol very often. It's called a messy protocol. There's an E state, and it's not quite as messy as a real-world protocol is, but we will see it's quite messy already. And the common optimization is to add an exclusive state. Okay, so what does that mean? When I'm in the initial when I'm in the invalid state and I issue a read, sometimes I may be able to realize that I'm the only node in the system to get this data, and this happens a lot. Even in parallel programs, you have private data, data that is private to one thread. Think about the stack data structure for the thread running on a particular processor. And it would be silly to have to go through this transaction of invalidating or trying to invalidate any other copy, not finding any. So since it's so common, why don't we realize this up front, that when we're reading from the invalid state and realizing, never mind how, we'll get into how later, but let's say we know that this is the only copy. So instead of going to S state, which is kind of a lower right state, we don't have the right to store the data, to write to it. We don't have the privilege. But if we know that this is an exclusive state, or we have the only copy, then we can write to it without trying to invalidate others. Okay? So that's good. The only difference between E and M is they both have the privilege to write, but in E state, you haven't written to it yet, so upon eviction, you don't have to write back. You just drop it as you would for a cache line in S in shared state. So this would be a special state called E, and it would be slightly different. So if you add this state, and if we can move the M a little bit to the right to leave space for the E, we're gonna add the E, so it's going to be like that. So we're gonna look at the new lines, transitions that were added. And again, it's here. Pause the video, think about it. What would happen? We're not showing all the action in the slide. Pause and think about what needs to happen if we're in I state, invalid state. There's read, write. What if we're in any other state and there are read and writes? Okay, so when we have a read from invalid state, which state do we go to? If you look at the state diagram here, a read transaction, we can go to S and E. So what does that really mean? That's two possible state, right? This really depends on what we found out from the system. When we read from the system, we assume for now that some mechanism will tell us whether you are sharing the line with others or not. If you're sharing the line with others, you go to the shared state just like before. But if you're the only one, you're not being shared. And that's what S bar is trying to indicate over here. Then you go to the E state. E state is sort of in between S and M. It is in between S and M. So if you read, that's fine, you just read. When you write, you go directly to M. That's the difference between the shared state to M, okay? In the shared state, when you go from S to M, you have to do all this external action, the invalidation. When you're in E state, you don't have to, because you know you're the only person having the data, okay? And finally, if there's an external read transaction, you have to downgrade yourself from exclusive state to S, because now it's clear you're no longer exclusive. So that will complete the state transition diagram. Again, think through this, draw it yourself. It will help you understand. Nothing is very difficult over here. It's just making sure everything makes sense. So we have these states. That's what we need. Okay? Without the state, we wouldn't be able to know when to invalidate, whether to invalidate, or when to intervene. Okay? The states, we know how to build them. Just a couple of bits per cache line, metadata. Okay? If we have two bits, we can represent 4 states. If we have 3 bits, we can represent 8 states. It's a finite state machine. We can do that. So how do we implement that? Well, why don't you think about this? And here is the assumptions. We start with something very simple. Okay, it's a write-back cache. We know those are typically more efficient than a write-through cache. And we start with a bus-based system. Okay, so this is a bus. Everybody is connected to the same bus. You have some caches on the next level, be it an L2 or memory, is connected on the other side. This is physically shared by a couple of processors. Maybe there's I/O devices. We don't care about them at the moment. And it's a simple bus. Okay, it's what I call an atomic bus. We'll see. This is in contrast to a later concept that we will introduce, a split transaction bus. In an atomic bus, a transaction is atomic. Okay, you get to the bus, you finish your business. You don't wait for, you don't split your transaction into multiple components, finish one component, let someone else get the bus, and later you grab the bus. None of that. Simple. You go to the bus, you will get the data you want, or finish invalidation you want. So just imagine this particular platform. Okay, you have your baseline system. You have your cache with its cache controller. Okay, it will read the tag. It will decide if it's a hit. It will know whether it's in one of the states, and it will try to do something. And the bus is a bus. You have wires to drive addresses on, wires to drive data on, and therefore we assume you can snoop into other caches. Okay, what that means is, you know, if you want to, when you're trying to write a cache line, you can go into other caches, or at least tell them, check your cache. Do you have this line? If so, invalidate. That's what we want to do, right? Think about what physical devices you need to make that happen.